I think we can start now. Once again, good evening, everyone, and welcome to this NXP Campus Connect program. I'm just repeating, as you are aware of, we are conducting this program on every first and the third Tuesday every month. First Tuesday is, dedicated for the SoC or the VLSI technology, and on the third Tuesday we are, mostly picking the topics from the system engineering part. This year is going on the IP year. So we discussed a lot of IPs in the past. And today we are going to discuss the Ethernet IP in automotive. What is special, we are going or we are, designing around this regular Ethernet so that we can use this in automotive. We have our presenter visible on the screen, Mr. Rajesh Udenia. Rajesh, welcome to this forum.
Thank you, sir.
Rajesh is our senior principal engineer, and he is leading multiple IP design projects in NXP. He is having total 20 years of industry experience, and out of that 12 years, since last 12 years, he is associated with us. And he designed and developed a lot of complex IPs. And today he is our, presenter who is going to discuss on how Ethernet is going to be used in automotives. So over to you, Rajesh. Just before giving you the control, the audience is mostly from college students, so they have a lot of queries in their minds, and maybe few NCZs or the interns from NXP. So this is the audience. Guys, please, you can type your questions in the chat box, or maybe after the presentation you can ask the queries. So we'll follow this rule. So over to you, Rajesh, now.
Thank you, Manish. Thanks for giving a nice introduction. I wasn't expecting that, but that's really nice. Thank you so much. So as Manish said, that today's topic is Ethernet in automotive. And as you know, Ethernet is primarily used in the communication networking. Uh, where it is very widely used, and in fact in today's life if you don't have Ethernet, then probably it's you are missing something. But slowly this Ethernet network is getting place, and not only the place, it is a very desirable network in the automotive industry. So on this agenda, actually, I will try to cover the history of Ethernet, and then I will try to cover how this Ethernet controller basically we are using in our chips, and how we are developing the use cases and applications. And then also I cover Ethernet evolution in the automotive, and how this Ethernet packet basically travels, and what is the life of this packet in the automotive industry. Because I have been informed that that audience is basically college students, so I thought I try to cover as much as possible, especially topics which we are using in the industry rather than which are available in the books. However, some of the topics definitely will be from the because like basic Ethernet packet and framing, I will also try to cover that, but I will not go in deep because these informations is very much available on Google, and also they would be part of your curriculum. I'm sure these things will be part of your curriculum. So agenda is there. As I said, I will try to cover mostly things which we are using in our industry. And then after this, we will take a question and answer, and I will try to address your queries. And if there would be any dilemma, or if I would not be know about them, then probably I will check them and get back to you. So this is the agenda of today's presentation. So Ethernet evolution. right? And I'm sure you knows about this thing. It was Robert Metcalf who invented this Ethernet technology, but it wasn't suddenly it came in his mind and he developed this technology. Actually, there is some history behind that. And the Robert Metcalf, he was working in the Xerox, and at the time frame of 1970s, and that time Xerox basically faced a problem, and the problem was Xerox was having some personal computers, and they were also having printers, but somehow they were not having a network or a medium through which they can connect their computer network computers with the printers, and they were not able to take these printers, and they were not able to connect their computers with this. And so Xerox management decided to assign this problem to Robert Metcalf, and it was because Robert Metcalf earlier during his graduation time frame, and also during the other research work, he worked on a Aloha net communication network, which was used for the radio communication. And from there, actually, so Metcalf used that technology, and that's why Xerox was aware about that. So they have assigned this problem specifically to Robert Metcalf. And so he developed this network, and he coined this name Ethernet. Ethernet, basically, this term has been taken from a luminiferous ether. That was a physics term, and it was basically used that time for transmission medium of the light. So he took the ether, and then it was a network of cabling. So he coined this name Ethernet. Uh, l- Once he developed this technology, Xerox basically patented that this technology, but they were aware that this going to be used very widely in in the world, and they wanted to open this technology, and they wanted to develop more product on this. So they have joined hand with the known corporation, Digital DEC Corporation, and the Intel that time, and they form a consortium which developed the standards as well as the product on the Ethernet based technology. That time, this was 10 Mbps Ethernet. Later, they have developed more and more structures, but as this technology came in the market, other corporations, houses also worked on that, and at the same time, IEEE also realized that probably they need to standardize this structure. So all these things have been done, and IEEE around sometime in 1983 standardized this Ethernet protocol, and that basically named as IEEE 802.3. And in fact, in this IEEE 8023, if you see this 80 is nothing but basically this work has started in 1980s. So it has been taken from there. And then 802.3 and other protocols, you already know they are available in this. So that's how it named. Now, this when Ethernet, when IEEE standardized this Ethernet structure, they have created a frame structure, and if you see this, this part basically MAC destination to FCS. This was basically DICS consortium, which was formed by DEC, Intel, and Xerox. This was their Ethernet standard structure. But IEEE on top of that, in appended two more bytes, that was preamble and start frame. So frame structure is this. On top of this, they have appended these two bytes, and then it becomes the Ethernet packet. So this range varies from Ethernet frame for 64 byte to 522 byte, and this is basically a nothing but layer 1 or layer 2 protocol, and in the coming slides I will show you how this is layer 1 and layer 2 protocol. But this is the Ethernet frame structure, and they require the physical medium and the logical level layer 2 control logic. Then I will go in this frame in every field of Ethernet frame structure, but not in deep because that information is already available. So in the preamble, if you very closely look at this, this is a fixed pattern of 1010, right? And there are 7 bytes of this. And when this data travels, this is basically most significant byte goes first and then LSB. So it's a basically 55. So 7 bytes of 55 goes into the network, and then this basically indicates all the receiving nodes on the network that they need to synchronize because probably packet is coming. So they synchronize their cells with the in the network. And they stabilize these things. And then if you look at the SFD byte, this is not 55, same pattern. It's a D5, and especially the last bit. This bit basically breaks these patterns and tell the network that next byte is basically Ethernet frame, and that's how it started. So, and this travels on the network, and then SFD is basically a start frame delimiter, which tells you that next is Ethernet frame is coming for the receiving node. Then uh, immediately after the SFD, there are addresses in the Ethernet frame, and these address fields are destination address and the source address. So destination address is basic, and both are of 60, both are of 6 byte long field, and destination address basically signifies that whether this packet or frame is meant for that receiving node or not. And similarly, source field basically indicates that who has transmitted this frame. So receiving node can understand, okay, this packet came from that particular node. So these are the destination and source addresses. Then this is an optional field, and it was not in original Ethernet frame structure, which was developed by the DIX consortium. It was IEEE who optionally put this VLAN tag ID. It was 4 byte long field, and it can basically identify around 4096 VLAN field. However, some of the fields are reserved, but approximately 4090 VLAN ID are free to identify different node. And VLAN basically works at the switch level. There it is very widely used, and I'll also show you in next slides where it will work. So this is the 4 byte VLAN tag. Then there is a field length and type. If you look at the Ethernet 2 structure frame that was DIX, there it was type, but IEEE made two objective of this field. It could be either length or it could be type. So when the payload, which was the middle section, if you remember that uh, frame, so this was payload. If this payload length is less than 1500 byte, then this was basically length of the payload. But if it is greater than 1500 byte, then it becomes the type. And this type is basically indicates that whether it's a IPv4 frame, or whether it's a IPv6 frame, or whether it's a ARP frame or other thing. So that's how this length and type field basically distinguishes between these two fields. Then there is a payload. Minimum size of payload is 46 byte, and maximum it can go to 1500 byte. but this is as per IEEE standards. But in some cases, there are implementations where higher bandwidth, a higher rate is required, and more payload is required. There, this payload can go up to 16K byte, and these kind of frames basically called the jumbo frames. But they require different kind of implementations, and some distinctions is required. So that's also there. That I have especially told about the jumbo frame because there are communication protocols where we need more data to transfer in the communication world, and this overhead, basically processing overhead, this reduces the efficiency. So if you send more number of bytes in a packet, then probably efficiency will get increased. So that's why I mentioned about the jumbo frame. Normally, it is not used in the automotive, but yes, there is the provision. Then the frame check sequence. This is the 4 byte field. This basically tells you about the Ethernet frame sanctity, whether this frame is intact as is when it was transmitted or during the transmission, because it will come through some physical medium, uh, through routing through different repeaters and physical medium. So when it reach at the receiving end, these FCS byte will tell you whether data is intact or any corruption has happened. So FCS, when FCS is calculated, they use a algorithm that is called the CRC, that is cyclic redundancy check algorithm, and that was used to generate the 4 byte FCS field. Then I use these 3 terms here. They are related to basically addressing, but I used because these kind of things we used very frequently in our applications. So one is unicast. Unicast is nothing but it's a basically point-to-point communication. One node communicate with the another node. If you have a network, there are hundreds of node, but other node will not know what the communication is happening between one to one. So that kind of addressing is called unicast. Then broadcast. Broadcast is something where you want to transmit information and you want that everybody knows about it. So you broadcast that information. So it's a kind of one to all. Then the multicast addressing. That is basically where you want a group of node know about the information, but not all. So that is called multicast. But if you see this distinguish happens on the addressing. So there is a destination addressing, there is a bit field, and when the this bit is uh, 0, then it is individual. Then if it is 1, then it is grouping. So there is, and also there is protocols where address resolution protocols, they identify these kind of things, and then also you need to do this. So but these 3 terms we very frequently used, and that's why I try to mention here. Then different types of speed. There is a lot of speeds are available in the Ethernet, and as the technology is growing, as the demand of bandwidth is growing, this speed is increasing day by day. But as I said, Ethernet started from the 10 Mbps data rate. At that time, it was sufficient, but nowadays it is not sufficient because we are having very advanced technologies. So the other speed which is available in the network, that is 10 Mbps. Then and this 10 Mbps Ethernet is basically called the fast Ethernet. After that, there is 1000 Mbps, that is called gigabit Ethernet. And there is also 2500 Mbps, that is called SGMI, or 2.5 gigabit Ethernet. And in coming years, you will see Tangi is available in the network communication network, but in even in the automotive industry also, you will see applications where we need 10 gig speed. and that is going to be implemented very soon, because the way industry is moving towards self autonomous driving and ADAS applications, we need these kind of applications. But currently we are using 10 Mbps, 100 Mbps, 1000, 2.5 Mbps speeds. Then cabling. If you in fact in coming slide I will show you in the ether in the car we never imagine that. So there is huge wire cabling between ECUs, and it's a full of wire basically network there, which are our proprietary standards. But when we go for Ethernet, we require different special kind of cables, and these cables should be able to handle that data rate. And that's why if you see 10 base 2, we use thin twisted pair cable coaxial cable, and 10 base 5, there is a coaxial cable. That 10 basically indicates the speed of the cable. 100 is 100 Mbps, 1000 is 1000 Mbps. T is basically twisted pair. F is basically fiber. Then SX, when it comes to the 1G speed, right? Then fiber comes in the picture, and you start using short wavelength or long wavelength for that kind of data transmission, because data speed is higher there. So we use these kind of cables in our chips validation, and during the testing of these 10 or 100 or 1G data rates. Then how these Ethernet basically will work in our silicon, what it requires. So this if you use simply Ethernet controller, it will not work. You need some phi. That phi basically it takes your data and transmit to the physical medium. And so in the Ethernet controller, there is a back controller basically which does, or which creates which basically takes the data, encapsulate in the Ethernet frame, and then transmit this data. And then it comes to the phi does the different kind of auto negotiations with the physical medium, and then transmit this data over the physical medium through after doing some kind of encoding and serialization and deserialization kind of thing. But these files, so there are various kind of file, because as I said, there are multiple speeds. If you are using 10 Mbps, then there is MII mode. If and these mode basically in coming slide I will show you, these mode will require the different kind of number of pins, and depending upon that they work. So MII is 10 Mbps, then RMI is 10 Mbps, but this is reduced. So number of pins will reduce when you go from MII to RMI. Similarly, in the GMI case, this is 1 Gbps, and RGMI, this is also 1 Gbps, but number of pins will reduce. And in the SGMI, these pins will drastically reduce, because this is a serial interface. They will require 4-bit, 4 pins, 4 signals. Then it will reduce to 2. Then it will be a simple differential wire. So these are the signals basically when you transmit the data from the Mac, which I have shown you on the previous slide, Mac controller, the and the phi. In between of these are the signals, and they depending upon the mode which you are using, the speed which you are using, these signals will be available. For example, in the HDMI case, it's a differential pair of cable, nothing else. No, but if you go in the GMI, you would require eight pins for transmitting the data. And similarly, in the case of receive side, you would require the eight pins of MAC, and these pins will be connected to the PHY. In the RGMI, this MII 3 Mbps and RGMI 4 wire, and then if you go on the RMI side, then it reduced from 4 wire to 2 wire, right? Similarly, and these are the associated signals. Whether when you transmit the data, you will transmit the enable signal to inform that these are the valid data. So these kind of signals will be there. Then definitely clock will be there. When you transmit the data to PHY, you will also give the clock, and this data must be aligned with the clock. It should not be beyond a range. Otherwise, it will be unaligned, and you will not be able to recover, and it will generate the error. So these kind of the signals, if you see here, these signals are available and they will be correct. So this I have shown you. Uh, this is RMI interface. This is normal GMI interface. This is RGMI interface. So there are basically two options. This I am presenting from that point of view. Let's say if you work on the Ethernet controller and you want to integrate with the PHY, then how will you integrate it? How the data will be transmitted from your controller to the PHY, and then it will transmit it to the transmission physical medium. So there are ways. Let's say so you have all the modes possible. And just one more thing, the PHY basically sometimes in industry, PHY available for only a particular mode. Let's say if you are using MII mode, then probably you will get a MII PHY. But there are PHYs which can support both mode. Let's say MII they can also support, and they can also support the RGMI or GMII. So if that is the case, then probably when you are transmitting the RMI data, then you need some kind of logic, mux logic, that can transmit this data, because this PHY can support both MII, RGMI, and GMI and MAC also. But pins are same, right? So you need some kind of mux logic which can mux these signals between RGMI and RMI and all that. So you need some kind of these kind of logic between this integration. There are scenarios where probably this mux logic shifted into the Ethernet controller, inside the Ethernet controller. And the reason is, when you integrate it, then you need to basically design the board, and board has the tracks for these connecting these pins, and there you need to maintain the timing, and you need to maintain the signal integrity, all these kind of things. So to avoid these kind of things, because on the board, if a track is running from one chip to another chip, there is possibility some kind of crosstalk or glitch can generate over that signal, and that can corrupt your data, or it can unalign your data. So sometimes, uh, normally designers, what they do, they shift this logic inside the Mac, and inside after that they have the common pins on both sides, and they just use this signal integration. But in that case, basically, you need some kind of software control inside this Mac, where you can define whether you want to work on the RGMI mode or MI or any other mode. Then clocking is very important in this part, because you are working on different speeds, right? So Ethernet says that if you are working on MII 10 Mbps or 100 Mbps, in that cases, clock comes from that PHY. They have a source here, then this PHY basically generates the clock, they gets the data, then there is a CDR recovery mechanism which generates the clock and data both. So in the MII case, data comes from the PHY, and clocks also comes from the PHY. But in the case of RGMI mode, RGMI is very stringent in their time for their timing, and they very clearly says that if your data must be within 500 picosecond of clock. So that kind of skew need to be maintained. There, this IEEE standard actually gives you flexibility that you receive the clock from the PHY in the case of one Gbps data, but for the transmission case, you can generate your own clock and you can give the controller as well as the PHY. And the other thing is RGMI is basically it's a DDR kind of thing, because if you remember, as I said that it reduces the pin. So it uses both positive ways and the negative ways for the data transmission. And that's why in the case of RGMI, you would require a inverted clock of that should be 180-degree phase shifted. But again, that will be used for the transmission of the data on the negative ways. So these kind of clocking structure also you need to think what application you are going to use, what speed you are going to use, what mode you are going to use, and based upon that, when you use this Ethernet in your chip or SoC environment, you need to provide appropriate clock in the appropriate directions and appropriate. Then only you can able to achieve a correct data, and the and your controller can work. This is the MAC architecture. This is this basically all these sub blocks which you are seeing. This is inside the MAC, which is called the Ethernet controller. So how this controller basically gets integrated in the SoC, and as you know, Ethernet frame need data, where from where it will get that data and where it will send. So this PHY side is basically the line side, and this is called the system side. System side means where it gets connected with the SoC fabric, and there on the SoC fabric, basically you can have the memories. From these memories you can get data, but again there is you cannot directly go and just get the data. You need some kind of protocol which is basically AXI HY interface, and these interfaces works in different data bit. It could be 32-bit, it could be 64-bit, or it could be 128 as well. But you need this AXI HB protocol because on the other side where SoC fabric is there, there are other masters are also connected on that. So to maintain this kind of thing, you need this. And on the PHY side, this is the line side. So here you will connect your PHY depending upon mode, and you will get the data, and that data will go through this path. So both receive side and the transmit, they are separate path, and they work independently. And that's why you know Ethernet works in the full duplex mode. So it works both receive and transmission directions. And there is one more thing, that is PHY management interface, that is called MDIO interface, that is management data input output. That is very important for the communication between the Ethernet controller and the PHY. Let's say your PHY is working in three different mode: MII, RGMI, GMI, right? And if you want to change your Mac to kind of work in, let's say, from MII to RMI, then how will you do that? In the running system, you cannot go and just change your file, right? So there, through the software control, you go into this interface. Through this interface, you go into the inside the file, and you change the configurations, you change the mode, you change the speed and all that. And that's how you align both the things, and then it works. Then there is a slave interface. That slave interface is nothing but basically you can configure different configurations in the control registers, and also inside the Mac controller at different stages, there are counters. So you can read the counters value. That is basically uh, kind of statics that can tell you how many packets are transmitted, how many packet you have received, how many packet you have dropped because of incorrect CRC. So that kind of information you use this slave interface, and that basically go and just read and write the control registers and status registers. Now, when you receive the packet from the PHY, it goes into this RX control path. There you basically remove the SFD and preamble, and you check the destination address, you check the MAC source address, and you decides basically whether they are correct packet or not. If MAC destination address is not correct, then you just drop that packet and wait for another packet. But if that comes here, then it goes to the some kind of parser mechanism where we change where we checks its packet sensitivity at higher levels, and then there is some kind of FIFO which transmits this packet, and through DMA controller, the Ethernet data goes into the memory. That memory normally we use DDR for keeping this data. And similarly, when we want to transmit the packet, we get that data and it goes into the TXDMA. TXDMA basically, okay. So you see here RxDMA and TXDMA, right? In the Ethernet controller, there is a mechanism concept called descriptor. So descriptor is kind of a link listing feature, and it has the information related to that packet, kind of like from where you will get that data, how many bytes you will read from that memory, whether you will enable the timestamp feature, whether you will enable the I mean timestamping. These kind of things are available in that descriptor, and these descriptors are separate. For TX that is separate, for RX that is separate. And these descriptors used by these DMA, and they read them, and based on that they get the data and form the Ethernet packet and transmit to the TX control. There FCS block basically it takes all the bytes into the account and generates the CRC checks, and there and again, and after calculating that CRC, it place into the Ethernet frame and then transmit to the PHY. There is one more important thing that is very important, and that is pause frame. Pause frame is nothing but, if you just imagine that there are two node and one node is continuously transmitting data, but you are not able to receive that because you don't have that much of memory or something like that, or there is any other limitation. Because of that you cannot accepting the data. In that case, how will you inform that node that you stop for some time, and after that you will send the data once I'll tell you, right? In for that kind of thing, that kind of application, that pause frame is very important. This receiving node transmit a pause frame, uh, uh, and that pause frame has a different kind of type field. On the basis of that type field, it identified that this is a pause frame. Then there will be some field, pause quanta value, that if that value is greater than 0, it means that you need to stop the packet for that particular bits number of cycles. And once it reduces to 0, or maybe in between of that, let's say receiving node sends one more pause packet with this pause quanta value 0, then it indicates that now you need to restart the transmission. So that also very important. There is one more thing, is the magic packet, that is for backup kind of thing. So what is the backup kind of thing? Basically, when let's say your Mac controller doesn't have any packet, or doesn't receiving any packet from the other end, then it goes into the low power mode. Actually, in the SoC or in today's world, it is very, very important that you save the power. So it goes into the low power mode and in the sleep mode, or you can say sleep mode. But when the packet, when the transmission starts, they send the magic packets, and it has also a different kind of type, and it there are continuous 6 or 16 packet, and that indicates, that will inform this Ethernet controller that now transmission is going to start. You wake up, and then again it start receiving the things, and it will bring all these things in the active mode. So that's how this Ethernet controller works. Yeah, definitely it requires some kind of memories, because it can have a packet in the store and forward mode. If it is using store and forward, then it will store the for packet first, and then it will do the processing, and then it will send. So there you need both memories, receiving side as well as TX side. This is this is a block diagram of one of our chip, and there you can see that we are using 1 gigabit Ethernet port, but at the same time, same controller we are using for the Ethernet router as well. Router, where basically we do the packet processing and forward it to us. Here you can see there are three different port, and there one is 1G, 1G, and 2.5G. So different speeds and different, and this is the fabric, and where we have the memories here, and they communicate with this DDR memory when they need to store the data or retrieve the data for the packet transmission or receipt. So this is one block diagram. Then this I have already shown, that this is our routing engine, where we are having three MAC port of different speed. Then we have some kind of security mechanism there. Then we have time sensitive network applications and AVB applications we are running, and then some kind of firewalls and all that. So going forward, I will show you in the use cases how these things will work. So these are so some of the important application in the automotive is very important, especially from the real time data, because in the automotive world, when you are running the car, right, sometimes let's say you need to apply the brake. That kind of data, that kind of communication between the decision making body inside the car and the brake, because as you applied the pedal, you push the pedal, and then this brake should apply, and that force should applied on the tires, right? That should be critical operations. So I'll show you how this. There are four features for the automotive Ethernet. They are very important. One is receive parser kind of thing, that as I have seen, whenever you receive the packet, you can you must identify whether you need to accept that packet or reject that packet. For that, you need some kind of algorithm and some kind of software control, where you can program these bytes, and you can match these program byte with the incoming packet, and if they are matching, then you can accept that packet and will do further processing. Otherwise, you can immediately drop that. Then time sensitive network, that is very important in nowadays, because as we are moving on the ADAS application. For example, just think of a car which is having the radar or camera, and let's say that camera detects a object uh, 20 feet away from your car positions, and once you detected that image, okay, there is some person or some animal, and you need to apply the brake, right? Then this goes inside the car, then decision happens, and that decision must be converted into the brake, and that brake has to apply within this 20 feet distance. So that kind of information, that is critical information. If you don't apply the, if you don't take the decision within that time, and if you don't apply the brake within that time, then probably you hit that person or animal, and it can be harmful for you as well as that object, right? So that kind of critical information must be passed at high priority. And time sensitive network is something which inside the automotive generate or develop that kind of ecosystem where you can do that kind of application. You can perform that kind of functions. To create this kind of ecosystem, it requires three main functions: enhancement for schedule traffic, frame preemption, time-based scheduling. Because in Ethernet, there could be different kind of different kind of traffic, right? Uh, for some people, it so it called quality of service, or sometimes it is low priority traffic, sometimes it is high priority traffic, right? What would happen if you get a high priority traffic, but at that time you are transmitting the low priority traffic, right? You cannot wait for the low priority traffic to complete, to pass this high priority traffic, because that is more critical, right? In that case, basically you provide some kind of reserved bandwidth or some kind of reserved slot, where as soon as you receive the high priority traffic, you can pass through that slot and it can go. But that alone itself not solve the problem, because sometimes just before the reserved slot, if your low priority traffic gets started, then how will you solve that problem? Then frame preemption comes. With this feature gives you flexibility that as soon as you receive the high priority traffic, you stop the low priority traffic, you preserve the signatures of that low priority traffic, keep it somewhere, and start the high priority traffic. Once high priority traffic goes after and complete, after that you again retrieve these signatures and start the low priority. So these kind of things you need in this uh, in the automotive car, and that can be developed by only this TSN feature. Similarly, media clock generation and recovery, this is also a critical application. This is called this is required in audio video bridge application. Think of that application where basically you have two video display inside the car and you are running the video, and speakers are in the car, right? But if audio and video they are not aligned, then will you able to watch that movie? No, probably not, because that is not in sync and that can annoy you, right? So to align them, these kind of things, we would require the media clock generation and recovery. And this is also one protocol where we do the network synchronization using some kind of sync message. And as you know, Ethernet is asynchronous, right? But in the network, one becomes the master and they circulate the information, and based on handshaking mechanism through packet exchanges, they try to synchronize with each other, and that gives you there. Then safety. Nowadays, it is very important that you have some kind of safety, because lot of critical information is flowing inside the car. There you need some kind of safety features where, let's say, ECC support or FSM timeout. Let's say somewhere in your design one FSM gets hangs because of any reason, then it should be there should be some mechanism which can tell the system engineer that, oh, that particular FSM is stuck and it will malfunction. So that system can come and take necessary action. So these are four important features. There are many other important features, but in today's world, in current time, probably these are more important. Now I will try to explain you how this Ethernet packet fits into the OSI model, and how this transmission packet transmission happens inside this. But before this, as I said earlier, this is the network inside the car. These are ECUs and they were connected like this. See, and in today's world, but they were vulnerable to the security, right? Anyone can go and just hack the system, right? But now, as demand is increasing, bandwidth is increasing, there is a gateway which is a central point. Only through this gateway you can go inside the car. You don't, you cannot go with other means. Similarly, uh, as complexity is increasing, we are dividing this car in multiple domains, and every domain has their gateways and then the central gateways. So we are trying to distribute this computation power, and we are trying to distribute or isolating that particular domain problems in that particular area only. That's how this feature is increasing, and it's this bandwidth and security is basically requiring the Ethernet. See here, lot of wires within the car, right? And this is really complex, and these weight of these wires also make the car bulky, right? So what we need to remove these kind of things, and we need some kind of simple structure. Sorry, some kind of simple structure. So so there is shared bus mechanism. They are basically they are connected and they are sharing that bus and transmitting the data from here and there. So what are all proprietary structures or lane protocols? So these are automotive bus protocol which are being used inside the car: CAN, lane, FlexRay, SPI, I2C, ITC, and all that, right? So CAN area network, it is looks like this. Lane looks like this, where his master is there, and then slaves are connected. Then FlexRay, then this is SPA interface, then I2C, and then Ethernet. Right? It's in mesh topology, star topology, ring topology, and all these things. Why? And see here in this chart, if you see, all these networks are being used inside the car, but no network is able to give you that much speed in today's to meet today's requirement. Bandwidth requirement is very high in automotive nowadays because of ADAS applications, because of self-driving automation kind of thing, and for the for onboard diagnostic purpose as well. I'll also explain the onboard diagnostics. So this tells you why Ethernet is required. And in fact, but it doesn't mean that Ethernet will replace all these networks. No, they have their significance. There are applications where we need them, but for higher infotainment ADAS side, we need Ethernet. Think of a application. Why Ethernet? Why can't we use these kind of network? Think of a let's say you spec out one network, right? And you have put the camera, and that camera basically detecting the images, traffic signs and all that, and giving that information. Then these specs go for the car manufacturing. 3-4 years it will take, almost 3 to 4 years for this validation testing of these chips, and then for the production in the car and application in the car. And once the car come out, right? And if you think that, oh, same camera can be used for basically on road condition to check the road condition as well. And based on that road images, you can basically assist the driver, or you can have some kind of mechanism where your car automatically change the lane if there is a hole in the road, right? That time you cannot go and just change these network, right? But Ethernet gives you that flexibility because data rate is so high that you just upload or just develop the software, develop these things, and you can use the same hardware and can change. So that's why Ethernet is becoming more and more desirable to meet these kind of requirements. So uh, this picture is basically different issues, different domain. They have their own switches. and they are connecting with each other, and then that information is coming on the central gateway, and from there they are coming. And this OBD is onboard diagnostic. Through this only, this system only, you can go inside the car. There is no other way, and that is very, very helpful in securing the data and securing this network. So both bandwidth and security is driving the Ethernet requirement in the car. And believe me, going forward in next 5 to 10 years, everywhere inside the Ethernet, you will see the network Ethernet backbone. How this packet will transfer now, this Ethernet life. So as I mentioned earlier, this is a physical layer and data layer. Here, this Ethernet frame will work, but other applications for network transport, this also there. And system engineer or application engineer, they will pass this information through these layers, and it will go into the Ethernet frame, and then through the physical medium transmission, it will go in different domain. So it is not like this. As I said, if you want to send some information, let's say you have the ADAS domain sign of thing, right? If you want to send some information, then it will go to this switch, then it will go to there, then it will go to central computation, then they will do these some calculations and computations, and then it will come through this and this. So this kind of structure, for that we need the Ethernet network. So that's where this come. This is just 2 slides. Then how this data goes in the Ethernet frame. So this is, let's say you have some kind of data. This data will go there. Then you will apply header and then FCS checks on this layer. Then if when it goes to the transport layer, then transport layer applies their own header and trailers. And then when it will go to the network layer, where it will be used for routing the packet to different lanes, they also apply their own header and this, and then it will go to the Ethernet frame. So this is basically Ethernet data, and then this is Ethernet headers, MAC address, and all other things. And then it will transmit it in the form of 1 and 0. And similarly, it will go from here to here, right? Sorry. Now, this is one use case, which I was telling you, diagnostic over IP. Why you need the diagnostic? You need the diagnostic because you can track the performance of the car. And very one thing is very, very important, and that is emission control. You must maintain the emission of the car, and it should be within the prescribed limit that has been prescribed by the different regulators, and you must maintain. Otherwise, it can harm to the environment, it can harm to the other things, right? So how will you do that? You have lot of electronics there, so you need to track the performance each electronic component. And through the this diagnostic over IP, you go and you transmit the packet that goes inside the inside the vehicle, and from there you gets all these data, and then it gets converted. So application, presentation, and session layer, this will be used by the system or application thing. And then through the transport, TCP and UDP, you already know this is transmission control protocol. That is basically connection oriented. UDP is user data protocol, that is user datagram protocol, that is connection less. Then IPv4 or V6, that is for basically routing within the domain. And then you need Ethernet frame structure. There you will put this data, it will go and then process, and then you will. So diagnostic is very, very important. Not only this OBD port is used for the diagnostic purpose, it used for the software upgradation as well. It used sometimes it used to understand the driver behavior. Let's say if one person is driving the car so rashly, it is applying brake, it is changing the gear very frequently. All these things gets stored inside the vehicle network. There are devices which stores this thing, and then through diagnostic port you goes inside them, and you read them, and then try to understand what is he doing, and where it is faulting, or any other things. Then some kind of control information. As I said, there are many various control information available inside the vehicle network that you can retrieve. So you use the application, again the same applications representation session layer, where you program the things, you maintain, you create that kind of thing applications, and then you send that information using these layers, and it goes inside the, right, and from there you retrieve the data. Similarly, deterministic traffic, as I mentioned, right, in the when you are running a video stream, right, and if your video stream is not aligned with your audio, then probably it will annoy you, right. You will not like to watch the movie if it is if its video is late, and that can be possible in the ethernet, because you cannot guarantee that latency. There could be latency there, not because traffic is coming from various points, and uh, so there could be congestion, and then you need these kind of protocol where you go and establish these kind of applications, and you give them priority, you give them sufficient bandwidth so they can travel with minimum latency. And for that you need different protocols. For example, IEEE 1722 protocol, that is something basically that that takes this media packet and form this, and use for the uh, network synchronization, PTP, that is precision time protocol. What it does, it basically it synchronize all the nodes which are connecting on that network with one masters. One node can become the masters, and then they synchronize them. And again, this PTP mechanism is the same. There they will send the sync message. They will once receive node receive that packet, it will capture that time. Then master will again send a follow-up sync up message. Then receiving node capture that time, and using these to capture time, it will send one delay request form frame that goes to the masters, and master captures that time and send that information again. So they takes they exchanges the packet, and through and using this PTP packet they synchronize with each other. And once that synchronization happen, and when the data comes, there is circuitry inside the chip which generates this media clock, depending on, and some software gets involved that basically does some kind of processing on these capture times and the event, and then it generates a reference clock and align this video data streaming with the with the audio, and that's how it works basically. Then TSN, as I said, that is a deterministic traffic. It has to go at high priority. There should not be any interruption in the network. If you put that interruption, if it gets interruption because of anything, then probably where some function can do malfunctions, or some error can happen, or some function cannot be performed, right. So that's very important. And there, as I said, uh, frame preemption, time based scheduling, time aware shaping, these are different protocol which ensures that your critical traffic must travel with least interruption and least latency. So that's how these TSN, audio video bridging, and all these things are working over the Ethernet, and that's why most advanced technologies like ADAS, like self-driving, these are possible, and these things are playing very important role in the automotive industry, and in the going forward, and believe me, whatever you are using in home, that will be available, probably that kind of network you will enjoy in the car itself, where car is in the autonomous driving mode, and you are controlling your home applications, you are controlling your other applications. Not only this, I can tell you one example or one application that I can think of, and in fact, there are many papers on that. Think of a network in a city where we have a city traffic control center, and that is, and every car through this Ethernet network is connecting with all other net or cars and the command center, and that command center can directly send information to these cars to divert the traffic if it sees somewhere is the congestion. No manual intervention would be required. Through this Ethernet, this can be possible, and this will be possible, and this will happen. Not only this, there is a technology, and which NXP is working. Sorry, which you can find, where vehicle can communicate with other vehicle. Vehicle can communicate with a person who is carrying a mobile phone and using the data network. When vehicle can vehicle in the running mode, it can provide direct system performance to the main center. What is this? So what is the performance of that car? So these kind of applications are possible only and only because of high bandwidth, and high bandwidth in today's environment can be provided by the Ethernet only. So that's how I think Ethernet is going to change this automotive industry, and in fact, it changed a lot. And it is as we see more advanced technologies, and we will see more and more use of Ethernet with higher speed. 10G is going to be used, and there could be possible where we can go up to 40G. So that is also possible. So with this, this is just a summary of all the applications which I have shown earlier. With this, I close my presentation.